Thank you very much for organizing this conference, to the organizers in the first place, and thank you very much for inviting me here. I will speak indeed about some recent results on the Lorentz gas with infinite horizon, but I will mention my collaborator when I get there. To start with, I review some basics of the model. So I will talk about the Lorentz gas with infinite horizon and mention some of the results to explain the problematic phenomena with infinite horizon, the type of very different laws, stochastic laws that govern this infinite horizon case. So Lorentz gas with, in the end, infinite horizon, but I will also go over the finite horizon because this is the best way to introduce it. Finite horizon, and to start with, I will start with the one-dimensional case. So what is this? I will go over every single word from here. This is the unit mass particle. That moves and bounces elastically. In a periodic grid of scatterers. Okay, so the first thing I shall try to explain is the periodic grid of scatterers, and I'm in a one-dimensional situation. So what do? I consider a cylinder. This is, well, a cylinder, a tube. Okay, so this is a tube, a cylinder. Very periodic to start with. And I place scatterers periodically inside the grid. So let me try to have a picture here. These lines are not here, but I will explain why I need them. Okay. And let's do one more. Okay. So here, as I said, these lines are not here. These are for my help to draw this periodic configuration of scatterers, but they will play a role in explaining the model. So what do I have? So you let and this continues here and here. So I let a particle inside the tube. I shoot one inside the tube and say that I start here. This will continue its trajectory, say here, and well, this scatterer should have been as the other one. Okay, here, I don't know what it wants to do. It goes here and it continues its trajectory. Good. So now I talk about the periodic configuration here. Now, since I place this periodically, I can think of this as these boxes here. I can think of them as cells. And I can think of the analogy with a random walk. I just have like a random walk on Z and I can label my cells, yes? This is a tube, a cylinder. Yes. Okay, so I can think of this like cell 0, say, and cell -1, cell 1, and so on. Good. What else shall I say here? The fact that I have this periodic configuration of scatterers, so periodic, that actually tells me that I have the same dynamics in every cell. In every cell. What does the same dynamic means? It doesn't mean that I have the same trajectory in every cell. It just means that I have the same evolution rule, the same dynamics. So same evolution rule. And what else do I need to explain here? Okay, so I can think of, so now since I talk about dynamics, I need to explain the phase space of the dynamics in a cell. Phase space in a cell. Okay, so here I'm going to have, so this is what I shall give it a name, say M. The space M there is going to consist of position, a tuple of the 4 position and unit velocity vector, so Q position of the particle and the velocity, unit velocity vector. And since it's the unit velocity vector, here is really the angle that matters. And with this occasion, I can explain what elastically means. So I take one of these scatterers, let's call them OJ. OJ, I take one of these scatterers here. And well, in the first place, I consider the, so I have the normal and the trajectory. And I will have, so here I will have this angle, this will be the angle of incidence, and this will be the angle of reflection. Okay, and then the fact that I have the angle of incidence being the same as the angle of reflection, this is what is called elastic movement. Okay, now the fact that as I said, here I have a unit velocity vector. So another way of describing M here, another way of describing the phase space would be to consider the union of the boundaries of the scatterers, because this is where the collision happens, the boundaries of the scatterers, union of the boundaries of the scatterers, cross the angle minus pi on 2, pi on 2. Okay, and now I'm in the position to define a dynamics on this cell. So T going from M to M. This is the, well, the one-dimensional Sinai-Billiard map. Okay, and it is known that this map T preserves a probability measure which can be described in terms of the angle phi. Okay, not the angle of incidence, but some angle phi. In any case, T admits an invariant measure. An invariant measure. Let's call it mu. The precise expression is irrelevant here. Mu. Okay, so good. So now what I want to introduce is I want to introduce a function which is going to play a crucial role in what I'm going to say, which is the cell change function. Cell change function. Or if you want to think of it in terms of a random walk, just think displacement function. So cell change function, this is going to be a function which I will call kappa, that goes from the phase space M. In this case, since I'm in the one-dimensional situation, it will take values in Z. Okay, and this is an integer function. And this gives me, so kappa 0 of X is the cell number at time 0 times 0. And if I look at the kappa index nx, so this will be the ergodic sum of kappa composed with p to the j x. This is going to give me the cell number of time n. This takes integer values. So it will tell me exactly the value it takes, cell number at time n. the value it takes tells me which cell I'm in, time n. Okay, good. Now, there is a related function, which is like if I want to look at the distance between consecutive collision in R, which is very related to this function, but for the time being, I prefer to skip that and mention it eventually at the very end. Okay, so now let me go to making sense of finite horizon. This is exactly the situation I'm in. The situation I'm in here is finite horizon. Why? Because there is no line parallel to the grid of the scatterers, to the boundary of the grid of the scatterers, parallel to the boundary of the grid that doesn't intersect the scatterers. Which is equivalent to the fact that in this case, kappa, this function, this cell change function, is bounded. Okay, good. Now, maybe this is the right place to introduce this. I can still squeeze something here. In contrast, in the infinite horizon, what will I have? I will have a situation, this is of course just one example, where I place the scatterers like this. So no scatterers on the, so here I'm in the opposite situation. I can draw a parallel line that, a line that doesn't intersect the scatterers. So in this case, kappa not only that is unbounded, but kappa turns out to not be in L2 with respect to the measure mu. And this is the crucial phenomena which determines extremely different law in the two cases. Okay. Okay, so I think I introduced pretty much the basics. And now I can, this is larger. Okay, now I can actually go to the recalling some old results on the typical limit laws in the finite and infinite horizon. Limit laws. Maybe before doing that, I want to say one more thing. So I did, let me take this back. So I want to talk about the limit laws. I leave them there. But here I didn't say anything about the entire dynamics, which I think is important. Not because it's going to be the subject of my talk, but at least I can say some words about the entire dynamics as I go along with presentation of the old results. So far I talk about the dynamics on the cell, and if I want to look at the entire dynamics, I'm going to define another map. I take the M, in this case, since I'm in the one-dimensional situation, I take the M cross Z, this is my entire space, which goes to itself. And what do I do? Again, kappa is the function that tells me how I move along the tube. So I define P of X, and L is a number here. And then I will have P of X, and then L plus kappa of X, okay? And if I want to go with the iterates, I do this, where this is the ergodic sum which I introduced earlier, is there. Okay, now P preserves not a finite measure, but preserves an infinite measure. Mu hat, let's call it mu cross Lebesgue on ZD. Well, Z in this case, since I limit the whole thing to Z here. Though, so I shall say that I restrict here to the one-dimensional situation just because of the easiness of drawing pictures. The same thing can be carried in Z2 if you are on a lattice. I will not, the only reason I don't go into that is because of, it's much easier to draw pictures here. So limit laws, in the first limit laws, and let me say for the cell change function. Change function. Okay, so let me start with the finite horizon. Finite horizon. Okay, one thing I forgot to mention here, and maybe this is the place to put it, is because of the symmetries in the systems, is actually know that if I look at the mean of this function is 0. Okay, so in the first place here I have the classical CLT. I will have that kappa n divided by the square root of n converges in distribution to Gaussian with mean 0 and variance. Well, in this case is just sigma because I limited myself to the one-dimensional. But let me say this is sigma, where so finite horizon. Let me consider the situation. So I said here that everything is, so just think of Z2 the same way. Except that you are on a lattice, not in a tube. Okay, good. So here the determinant of sigma is going to be different from 0. Okay, and this type of, this was established long ago by Bunomovich and Sinai. Sinai in 81, I think. Okay, the only thing they had to do here was to, the thing that worked here was to compute the Green-Kubo formula. So this was one situation. Later on, people look at local limit theorem, and so throughout the talk, I'm going to think of ZD extension with D equal 1 or 2. For 1, I have the picture on the board. For 2, just think similarly. So here I will have something like, if I take square, this is the scaling, and I'm looking at kappa index n equals 0. Okay, and this will converge to, as n goes to infinity, this will converge to, I take, say that I call this random variable W, and I consider the density of this random variable. So this is going to be G of 0. So this is the density of V. W, sorry. Okay, good. Now, I shall mention here that once you have, I forgot to put some names here. So this local limit theorem was proved by Sash and Varyu in 04. Okay. And this local limit theorem is good because, well, it's an important phenomenon by itself, but it also allows one to look at the mixing for the entire dynamics. And basically, there is a way to read. I will not go into this bracket for too long. There is a way to read the local limit theorem, to read mixing from the local limit theorem. And this is a local limit theorem for the function, say, the indicator function of the cell of the cell M can be read directly from there. For general function, so let me put pen general function and fantastic error rates, functions and good error rates, and optimal expansions in mixing. And I think this is 0.7, but I'm not sure of the year. Anyway, so this is what I limit myself saying about mixing. And now one important thing, which is going to be crucial for me from here on, is what people call the strong invariance principle and the law of iterated logarithm. So strong invariance principle, or the so-called Strassen principle, or also called the almost sure invariance principle, which I shall denote by a SIP. Okay, good. Now, let me say the result directly for the finite horizon here. So I stress on the fact that here I'm on the finite horizon situation. Okay, what people proved, and I will put some names at the end, people proved that there exists a probability space where I can where I can compare kappa n with a Brownian motion almost surely. Let me say what that means. So there exists a probability space. Let's call it omega f1 p1. And two sequences of independent random variables, let's call them yj and zj. Okay, so that in the first place I will have, this is going to be condition 1, yj is going to be distributed as kappa, kappa composed with t to the j, where t is the billiard map. Okay, so they have the same distribution. The second thing is that zj here is going to be distributed as n0 and some identity matrix, so a standard Gaussian. And 3, and this is the main thing, is that if I look at the sum j going from 0 to n-1 of yj minus sigma, where sigma is the sigma here is exactly the sigma that I wrote there, the sigma in the CLT for kappa, sigma sum j from 0 n minus 1 zj. Okay, this is going to be almost surely equal with some sequence bn. So this is almost surely. And this bn here turns out that people prove much better than this, but I will not go into that. This is the square root of n log log n, the little o of this, log log n. Okay. Okay, so in other words, what this is, the message here is that on an enlarged probability space, which is that one, I can compare kappa n with this sum here. And what is this sum here? This is a Brownian motion at integers. Okay, Brownian motion at integers. Okay. So maybe even write this. The message is on an enlarged probability space. Enlarged probability space. I can look at the distance between kappa n minus sigma. Let me give this like a b of n, which is what I call the Brownian motion at integers, minus sigma bn. Okay, this is the little o of that bn. Okay, too many little o's. This can be a big O, of course, because I have that there. And what is one consequence here of this? This is called the almost sure invariance principle, and it was proved by several people by different methods. Let me put down some names. Okay, so some names here associated with this. So a shift finite horizon follows from several works. So first is there is a work of Chernov in 06. Then there is Melbourne and Nicol. Again, I think 06. Then there is a work which is going to be extremely important for what I will mention on the result with Peter later, with Peter Balin later on, Güzel 10. And then Korepanov several works. 20 and some other years, which I don't remember. Okay, so these are the people that look, actually there are many more that look at this. Merlevet, they also look at this, and many other people in different settings, and the AC for finite horizon can follow from different setups. Okay, and of course the matter for them was to obtain the best rate possible there. But for me, what I wrote there, it's enough, because I am interested in the law of iterated logarithm. Which I denote by Lil. Okay, and so the law of iterated logarithm tells me that if I look at that, so this is just ID situation, tells me that if I look at the sum J0 going from n minus 1 Zj, and I look at the lim sup here, and I take the modulus and I divide it by the square root. There is a 2 here, and log log n. Okay, this is going to be 1 almost surely. Okay, so putting these two things together, remember this is just the same sum as there, putting these two things together, one obtains the law of iterated logarithm for kappa n. Where shall I write it? I shall write it here. Okay. Okay, so consequence of a SIP of this almost sure invariance principle is that if one looks at lim sup n goes to infinity, modulus of or norm of kappa n divided by, well, n log n, this is going to be some number between 0 and infinity. I suppress 2 or anything like that. Everything is embedded due to the variance and so on. This is the result that comes out. Okay. And good. Now I presented everything I wanted about the finite horizon. Let me switch to infinite horizon. As I mentioned before, there is no, kappa is no longer in L2. So in this scenario, one cannot expect to have the CLT that I wrote before for kappa n. So in this case, what is known, and maybe I shall write this down, that the measure of kappa, if I take the norm of kappa or modulus of kappa, if I want to fit in the one-dimensional situation, greater than capital N, say, this is a constant divided by n to the 2. So if you look at this, this just fails to be L2 because it's just, if I had 2 plus epsilon, everything would have been fine. Okay, good. So now the laws that happen here are very, so I will say a non-standard CLT. Non-standard CLT. So what happens here is that, okay, I consider kappa n, but no longer I divide by, I need a correction here. I have n log n. And this is going to converge again in distribution to normal 0 sigma, where the determinant of sigma is different from 0. So I have an invertible matrix. Okay, in the one-dimensional situation, kappa being unbounded suffices for this statement. When I look at the Z2 extension, so in the lattice situation, I will need some non-degeneracy condition, but since I haven't presented anything, I skip that. So this is the phenomena that happens. And who proved that? So there are two proofs of this theorem, both of them proving stronger results, not only the CLT, but a refinement of the CLT, which is either the local limit theorem or, so a first result, see non-standard, this thing here, let's call it star. Star follows from, star was proved via, by Sachin Varyu in 07, who proved a stronger result, namely that if you look at the square root of n log n to the power d, again d is 1 or 2, and you look at kappa n equals 0, then you have again, this goes as n goes to infinity, goes to g of 0, where g is again the density of, let me call this again W for the lack of a better name, of W. So this is one one situation. And another refinement was done by Chernov and Dogopiat. In 09, who proved the convergence to Brownian motion. So they proved the Brownian motion. I will not write down the statement because it deviates from what I'm going to say next. People that are interested, happy to talk about after. So Brownian motion, but with this particular scaling. Okay, so this is another refinement. And okay, fine. I shall mention here, while I mention the local limit theorem, that without writing this down, that many other refinements were done in the, several other refinements were done in the infinite horizon. So in the first place, error rates for the mixing for the entire dynamics was done by Penn and myself. Then some other interesting phenomena like specific large deviation and so on by Penn, Melbourne and myself, Melbourne, Penn and myself. And that's about it. Okay, so the natural question, since I talk about the infinite horizon, I'm interested in an analog of this situation. So what happens in the infinite horizon? Can I have anything there? So this is, shall I erase this? Yeah, I think I will erase this. How am I doing with time? 10 minutes, okay. 12, oh, that's perfect. I can fit that in. Okay, good. So let me tell you what happens in the, so it's a natural question. What if you can expect anything like that, and what would that mean? Okay, let me consider now, deviate a bit from the finite horizon. It's easier to state the result in the some IID situation, and then tell what Peter and I did. So in the IID situation, consider a situation of the following form. You have xj, say, j greater or equal to 1, IID random variables on some probability space, whatever that is, omega fp. Okay, and now I want to look at the situation where I'm exactly like in the infinite horizon situation, where this just fails to be L2. And okay, let's just say, to assume everything as it is, if I look at the sum of j going from 0 to n minus 1, xj, again, let's assume here that I have the expectation of xj 0 to make things easier. So obviously I have infinite variance, infinite second moment. And here I have, again, let's assume for simplicity just this. This goes in distribution to some and 0 sigma, where sigma is positive. Let's consider that I have real random variables to make the whole thing very easy. Okay, so in this situation, let me call this situation here, refer to it as 1. People like Aymal look at it in several papers to obtain, in the first place, a form of the almost sure invariance principle, and then as a corollary, the law of iterated logarithm. So to be able to state the result, I need to consider a class of sequences, yes, a class of sequence is Cn n greater or equal to 1. And this I will denote by some hypothesis. So in the first place, I will consider that Cn is non-decreasing, And the main thing that I need, and this is very intuitive to state, I need that if I look at the sum n, and if I look at the probability of xj being greater than Cn, I want this to be summable. So this is the way I want to consider this class of sequence Cn. And what I notice here, now, one thing that is easy to say, if this sequence Cn would be exactly like this one, I would just fail to have the summability. So in particular, what I notice is that Cn on n log n, square root of n log n, has to go to infinity. Okay, and then the second condition is, I will not go into this, is some nicely monotone, is some technical condition. Okay, so this is the class of sequences that I'm working with, and I want an analog of that situation there. Yes, these two conditions. Any Cn that satisfies these two conditions, but okay. So then here is the first result of Einmal. I state the result. So let me say this is theorem 1 of Einmal, which was done in several papers. Started from 88 and continued up to 207, several refinements. And here is the result. Assume situation 1, assume 1, and let Cn be as in C0, satisfy H0. Okay, then the same thing happens with what I said before. There exists a probability space. Let's call it again omega 1 F1 P1. P1 and two sequence and two independent sequences, two sequences of random variables. So that let's call them again Yj, two sequences Yj and Zj. Well, 0, since I want to do the sum from 0. Okay, good. And the result says so that in the first place, I will have that Yj is going to be distributed like Xj. So this means they are distributed the same way. And the second thing is that if I look at the sum of Xj, j going from 0 n minus 1, okay, sorry, Yj here, Zj has to be distributed. I forgot to say the Zj. They are distributed as n 0, 1, okay? And 3, which is the most important thing, if I look at the sum of j going from 0, n minus 1, and I have xj, here I will extract some gamma n, which is crucial here. And then I shall say in a moment what this is. N minus 1, Zj. Okay. And here I will have the little o of Cn. Okay. And gamma n, this is the crucial bit here. Gamma n squared is going to be the covariance or variance of, I take xj, one of these, or x0 simply, and I truncate it. x0 is going to be truncated at the level Cn. So the main thing here is how you choose the truncation here. Once you figure out how to choose the truncation, so this is a covariance metric, but you have to work all the way through with some truncated random variable. Without this truncation, it's impossible to compare to get anything like an analog of the ASIP. Okay, and the consequence of this is the nicely monotone. I refuse to, so if I look at okay, is Cn on Cm behaving nicely? That's so I said that there, the idea is that I want to compare this and to compare these things, but on a larger probability space. So in the first phase, so yj, and the message here that I can compare xj with this, but I need a larger probability space for that. Sorry for the typo. Yes. Okay, so the consequence of this is that I have a law of iterated logarithm. So in this particular situation, let me cut the whole thing short. So in this particular situation, a consequence is that I will have the so-called generalized Lil, which is trivial Lil. Okay, so I will have that if I look at the lim sup n goes to infinity, and I consider the modulus of the sum j going from 0 n minus 1 xj divided by Cn, this will converge to, this will be some number A, but the problem is that this can be 0 or infinity. So in general, this, obviously I don't want a trivial statement. So in general, it's impossible to satisfy, to get an expression of Cn and A. Not only it's impossible to guarantee that you don't have a trivial statement. One situation in which this works, so in general, nothing. In particular situations, in special situation, and I would devise one here to fit with the infinite horizon, special situations. In special situation where I further consider, so let's suppose that xj, now to simplify the statement, goes from the same space gamma, omega, but takes values in z, not only real, but is a real value. And I assume something more. I assume that if I look at the density, so the probability of xj being precisely n, this is some constant on n to the 3. So I have a precise formula for the density here. In this situation, it's possible to determine both Cn and A. So in this special situation, which I shall call 2, in 2, the Lil here, Lil, holds with Cn being, okay, it has a very weird expression. Some, the constant is exactly this constant, some 2c log n log n, and then 1 plus further log n, and I continue further here with some sine squared of something. You can ignore this. This is log n, but it doesn't matter. What matters is in this situation is that I can precise, I can give a precise expression for Cn and n, and actually guarantee that in this particular situation, the generalized Lille makes sense. Okay, and the result with Peter Balint, I shall state it as a theorem to end with. The result with Peter Balint is that we generalize this to the infinite horizon, but I have a couple of minutes. Okay, so theorem 3, Balint and myself. And we showed that theorem 1 and well, generalized Lille, holds with Cn of that form there, with Cn as in as exactly there is Cn as above, and okay, not exactly a equal 1, but a in 0 infinity. Okay, now the hard part, and here I will not write anything. The hard part was to prove the generalized ASIP. That is to get a form of this type of generalized ASIP. This was the hard part. We couldn't borrow anything from the IID situation. What we have done there, we have well, use the Guzel method, so well, some spectral methods, some transfer operators in between, but that's irrelevant. So there we had to work very hard. And along the way, we had to do two crucial things: truncate several times, not only with Cn, and improve the fourth moment for sums of partial variables, truncated sums of partial variables. In particular, so along the way, let me say this, along the way, we actually showed that if we look at the integral of kappa, we take some j going from 0 n minus 1, kappa composed with t to the j, and I multiply it with the function kappa, well, truncated by some r here, and I look at the fourth moment, we show that this is essentially less than some constant R2, which essentially means that we got rid of a lot of logarithmic factors from previous estimates by Chernov and Logopiat. And I think I stop here. Thank you very much.
Are there any questions or comments? I have, yes? Yeah, please.
In terms of the spectral, becomes more complicated. What becomes more challenging to prove?
Yes, so in terms of what we had to use there essentially is we had to verify the correlation condition at the level of characteristic function. So we had to divide the whole thing in blocks, because this is how you use the method of blocks, and you had to work with verifying some decorrelation condition at the level of blocks. Now, due to the truncation, we had to work a bit harder, but that wasn't the hard part, adapting that method in some sense. The hard part is that the method was designed to work for the classical CLT situation. So we had to redesign it at every single step.
Are there any other questions or comments? Here. Corina.
So double questions on this Cn. If you can give any idea where do they come from, this cross? And also you said this is a non-degenerate case, but you could have some degenerate case where you have a 0 or infinity in the generalized. Do they really happen? Do you expect them to happen, or?
So if it turns out that with this particular condition, with this particular sequence, so in the first place, what you can see here is So if you take this, it satisfies the summability condition, which was crucial at some point. I think I erased it. The fact that I have the probability of xj being greater than Cn, that to be summable, because here I have, so what I want in the first place, I wanted the sum n, probability of kappa being greater than Cn to be summable. So it satisfies this thing in the first place. But in the generality of this situation, things you cannot guarantee that the limit is not zero. To determine, to actually prove, it turns out that you really have to compute the sequence precisely to ensure that you don't, this comes from calculation. It's several summability conditions that have to be satisfied along the way. But in the first place, this is the easiest thing to say. It satisfies this summability condition nicely. And yes, I think that's what I can say in simple terms, unless I go to the method of proof. But the crucial thing here is that the hard part of this is that you have to figure out, even for a natural ASIP, let's forget about the generalized, the law of iterated logarithm, these come together. This is, you have infinite variance, which is very different from the stable law situation, for instance. There you have a single outlier, you know exactly what you subtract. Here, you have several ways to truncate. You have to balance this and this come together, and this is the difficulty of the statement.
Next speaker is Reila Zheng. She will talk about Sharkovsky ordering on the Mandelbrot set. Thank you.
Thank you for the introduction. So my talk is going to be on Sharkovsky's ordering on the Mandelbrot set, and this is a talk on complex dynamics. So a bit of background. What I'm concerned about are quadratic maps of the form z squared plus c. So if you consider a quadratic map, you can define the filled Julia set as the set of points such that under iteration of this map, those points remain bounded. And these are some examples of the filled Julia set. Even though it's a filled Julia set, it might not necessarily have interior. So the Mandelbrot set is a subset of the parameter space, that is a set of the parameters C, such that the filled Julia set is connected. So the motivation for this problem is we're going to consider the ordering along veins on the Mandelbrot set. So maybe let me just draw a cartoon of the Mandelbrot set. So you have all these components. And so forth. So if you consider a vein in the Mandelbrot set, let's say the real vein, that is some sort of arc that's in the Mandelbrot set, and you consider along this vein traversing towards the main cardioid, what can you say about the components along, the hyperbolic components along this vein? So let V be a vein in the Mandelbrot set, and along this vein V, let's consider the components of period n, and we're going to define C sub n to be the component of period n that's closest to the main cardioid if it exists. So you can, for instance, if you look at this diagram, I've colored, or not that I have colored, Mandel has colored some of these components. So the dark blue one is a period 1 component. The light blue are period 3 components. There's also a smaller period 3 component on the real line. The green is a period 2 component. The reds are period 4, etc. So what can you say about the ordering of the dynamics of these components along a vein? Any questions about the setting so far? Is this okay? Okay. So I'm going to first give a description of some of the things that I'll need to talk about in order to solve this problem. And one of the first things that I'll consider is the Hubbard tree. So given any parameter C, and given the filled Julia set, so for instance, I'm going to draw the rabbit. So you can define the critical orbit. So you have the critical point, 0 maps to C, and then eventually maps back to 0. And there is a sort of unique way of connecting the points in this critical orbit along these minimal arcs such that you get a tree. And the dynamics of your map on the plane restricts to the dynamics on a tree. And in some sense, the Hubbard tree captures all the interesting dynamics of your map. So we're going to define the Hubbard tree for any parameter C. And we're just going to look at the periodic points on this Hubbard tree this Hubbard tree. And the map restricts to a map on the Hubbard tree that maps vertices to vertices, and it maps edges to paths between those vertices. Another thing that we're going to need is, I'm going to talk about orbit portraits. And basically, in order to define that, whenever you have some sort of set that's topologically a disk, you can always uniformize it to a disk. And in particular, if you have a Phil-Julia set that is connected, the external can be uniformized to the external of a disk. So you can define things like external rays. And your map acting on the external region is going to be the map Z maps to Z squared on the disk. So you can just talk about the dynamics of these sort of rays under the doubling map. So let me just sort of skip this. When you do this uniformization, there is a way of associating the uniformization in the dynamical plane, the external rays in the dynamical plane, with the external rays in the parameter space of that hyperbolic component that your map comes from. So let me just sort of skip this. And the reason why we need that is to describe the sort of orbit portraits that we have. So given a periodic orbit, such as the one that I've written, you can sort of describe the orbit, the periodic orbit of it with the orbit portrait that consists of the external rays that land at each of the points in this orbit. So the orbit portrait is just going to be a description of the sort of angles at Z0, the angles at Z1, and et cetera, et cetera. And the reason why we need this is because in the parameter space, what happens is you have the sort of nestedness of the orbit portraits. So for every admissible portrait, there is a sort of region in the parameter space that corresponds to all the parameters that will have that orbit portrait. And only the ones within that wake will have that orbit portrait. So for instance, let me try to sketch some nested wakes. So for instance, this blue one is going to be the wake that corresponds to the portrait with the critical angle 1/3 and 2/3. So there's a specific period 2 portrait. There's a specific period 4 portrait that corresponds to the green region, and so forth. And the thing about these these wakes is that the wakes are always either nested or disjoint. Any questions about this? Okay. Right. So now, Sharkovsky's ordering, which was in the title of this talk. So the classical Sharkovsky's ordering describes the sort of orbit forcing of a continuous map on an interval. So say that you have a continuous map on the interval, and if you have a periodic point of period n, and this is exact period n, you can say a statement about orbit forcing. So if per f is the set of natural numbers such that f has a point of period n, then, for instance, you can say the following statement. If it has a point of period 3, then it has a point of period n for every natural number n. This is a classical fact, and moreover, there is an ordering on the natural numbers. If there is a point of period 3, it implies there is a point of period 5. If there's a point of period 5, it implies there's a point of period 7, and so forth, all the odd ones. And any of the odd ones implies there is a point of 2 times 3, which implies there is a point of 2 times 5, and so forth. And then you have 4 times the odd numbers, 2 to the n times the odd numbers, and so forth. And after a countable number of these, you have 2 to the n, 2 to the n minus 1, decreasing all the way down to 2 and 1. So this is the sort of classical statement. And Sharkovsky's theorem says that if you ever have some number n that's larger than m in this ordering, and if f has a point of period n, then it has a point of period m. Moreover, for any tail of this order, so the set of periods of f is going to be a tail of this ordering. That is, it's going to be some, the rest of this ordering. And any tail of this ordering corresponds to the set of periods of some continuous map on an interval. So I'm going to denote this ordering by less than subscript 2. And because I'm going to talk about the ordering on a tree. Yes? Yes, so there's a component here of period 3. And this is the component that people in complex dynamics call the airplane. The dynamics of it looks like this. So you have 0 maps to that point here, and then it maps back like this. And there is a fixed point, the alpha fixed point here. Okay, so moreover, the other thing that I'm going to say is that in this ordering, you have what are called Stefan cycles, and Stefan cycles are essentially these cycles of odd period, where you have some point that maps to some point over here, and it maps to some point over here, and so forth, and you have this sort of like spiraling outward, and then eventually maps back. So this is what a Stefan cycle is. And whenever you have the largest period is of some odd period, 2k plus 1, then this map has a point of period 2k plus 1 that is a Stefan cycle. Yes? Can I explain this ordering? You have the odd numbers, then 2 times the odd numbers, then 4 times the odd numbers, 2 to the n times the odd numbers, and then you have powers of 2 decreasing. Okay, so you can also describe the N-Sharkovsky ordering, which is the description of the partial ordering for continuous maps on a tree. And maybe let me just illustrate with an example. So if you have, let's say, the 3 Sharkovsky ordering, basically what you're going to have on top is you're going to have 4, which is larger than 7, which is larger than 10, larger than 13, and so forth, all the numbers of the form 1 mod 3, 5, which is larger than 8, which is larger than 11, larger than 14, larger than 17, etc., of the form 2 mod 8. And all of these ones are going to be larger than numbers that are going to be 3 times the usual Sharkovsky ordering. So you have 3 times 3, which is larger than 3 times 5, larger than 3 times 9, all the way down to 3 times 1, and down to 1. So in the sort of tail of it, you have 3 times the usual Sharkovsky ordering. And between these 2 branches, you're going to have 4 is also larger than 11, 7 is also larger than 17, 5 is larger than 13, etc., etc. So it's a partial ordering. Not every element can be compared, but you could, for any element, consider the set of elements that are strictly beneath it. So for instance, the set of elements that are strictly beneath 4 in this ordering consists of all the elements on this branch that are beneath 7, and all the elements on this branch that are beneath 11, and everything in the tail of it. And in general, in the N-Sharkovsky ordering, you're going to have numbers of the form 1 mod n, 2 mod n, etc., up to n minus 1 mod n on top, and the multiples of n here. Any questions about this? This is maps. This is going to be a description of the period forcing of maps on an n of a tree with n leaves. And sorry, the theorem is every continuous map on a tree with n leaves has the set of periods given by a union of tails of these I orderings with I less than or equal to n. Reason why you need I less than or equal to n is you can imagine a sort of tree where some of the leaves have this behavior where they map to each other and the other ones map to each other. And moreover, whenever you have a spiral graph, so that is a graph with n leaves, where you have vertices that map like this. So the vertices sort of map outward on all of the leaves, and then it eventually maps backwards. And the edges in between map homeomorphically to the path in between the vertex. So this is a spiral graph. So whenever you have a spiral graph with kn plus I vertices on n branches, then the set of periods is exactly the set of numbers that are less than or equal to that kn plus I. So yeah, so this theorem works for trees with n leaves, as in n terminals. Yeah, but all that I'm going to talk about from now on are going to be n-branched stars. So trees like this, where you only have a branching at the very center. Any other questions? Okay, so let me now describe the ordering on the real vein. So the first thing that we talked about is we have the real vein. Oops. And because we know that there is a component of period 3, the airplane, on the real vein, by orbit forcing, since the wakes, so this Hubbard tree is going to look like an interval, and this is an interval map that has a point of period 3. Therefore, by the usual Sharkovsky ordering, this has a point of period n for every natural number n. Now, because it has a point of period n for every natural number n, and because all the periodic points of any period is witnessed by an orbit portrait, and because the orbit portraits are nested, you can talk about the component of period n that is closest to the main cardioid and the corresponding wake for that component. So now, because we have because there's only finitely many points of a given period, the ordering of those components, C sub n along this vein, must be exactly the usual Sharkovsky ordering. If it's not clear why, you can just think about this a little bit. So that is C sub 3 is further away on this vein than C sub 5, which is further away than C sub 7 and so forth. And actually, you can actually see all these components that look like this. And moreover, all of these components, C sub n, where n is an odd number, the graph of that must be a Stefan cycle. That is, it must be points that spiral outwards like this, where we have the alpha fixed point there. So this is something that's not very hard to deduce. And we're going to use this fact to talk about the ordering on principal veins. So a principal vein is essentially, there is a way of generating a principal vein from the real vein, given by a surgery in the dynamical plane of the whatever parameter you have. So to give an example, let's say that you have some sort of component on this real vein. The way that you perform the surgery is that you break the Hubbard tree at the alpha fixed point, and you take that sector that does not contain the critical point. So the critical point is this point 0, and you duplicate that sector. That is, if I do that operation, what I can end up getting is this alpha fixed point, and I have this point here, this point here. I duplicate that sector, and I leave the critical sector fixed. So I have 0, maps to this point, maps to this next point, and so forth. So as you can see, if you do this, and you can do this operation any number of times, what you end up getting is a parameter on a principal vein. And moreover, that parameter is going to have the dynamical behavior of a spiral graph. So this next part is going to be, so you do this surgery where you sort of embed the real vein along any principal vein. So you can talk about the ordering of these components along a principal vein. So for any n-branched star, the ordering, because it's the Sharkovsky ordering, because it's a partial ordering, there's a question of how you're going to merge the two branches. And the fact that if you know that the graphs of a certain period are spiral graphs, whenever that happens, the set of all periodic orbits of it are exactly the things that are less than that in the ordering. So the way that you can merge the two is that you know that for the principal vein, you are going to merge them so that in a way that's coordinated by the 1 mod n branch. What do I mean by that? So let me just put down the 3 ordering again. So I have 4, and then 7, 10, 13, and so forth. 5, 8, 11, 14, and so forth. And we have 4 implies 11, 7 implies 17. So we know that 4 is a spiral graph. So the set of periods that this point of period 4 contains is everything here and everything here. And we also know that 7 is a spiral graph. So the set of periods that 7 contains is everything here and everything here. So since 11 and 14 have to go somewhere, they must appear in between. And likewise, the same argument can be said for 7. So after 7, we have 17 and 20 and so forth. So this gives the way of merging the different branches on this partial ordering. And my theorem says that the ordering of the components on a principal vein with n branches is exactly given by the Sharkovsky ordering, where we merge it in a way that the 1 mod n branch is used to coordinate the ordering. Any questions about this? Yes, yes. So my theorem is the ordering of the components on any principal vein, where I say the principal vein with n branches, meaning that I've done that duplication of that non-critical sector n-1 times, or sorry, n-2 times, so that we get a tree with n branches. So the way that when we say the statement about the ordering of the components along that principal vein, the way that the merging occurs is that they are going to be coordinated by the 1 mod n branch of the n Sharkovsky ordering. And that's this ordering of the numbers that I've given here, where there are all these implications going between the I mod n branch. And all the components of period 1 mod n are going to be spiral graphs. Any other questions about this? Is this okay? Okay, so that's the first statement that I have. And the other thing that I can note is that the internal address, which is the sort of combinatorial description of how you can get to the Hubbard tree of any particular component, is given by this. And just knowing the internal address is enough to deduce the Hubbard tree, and vice versa. Given the abstract Hubbard tree, you can deduce the internal address. So the internal address of any component of the form 1 mod n is going to be you have 1 and then n and so forth up to some multiple of n, and then you have the number km plus 1, where km plus 1 is the period of this component. So we're going to use this fact to get to the next step of my theorem, which is you can do an ordering on the non-principal secondary veins. So we have this sort of duplication of the real vein to get to these principal veins, but you can also get to these other veins, where these other veins are just, you can think of it as you follow the principal vein up until this Mizarevich point, at which point there are n-1 branches that bifurcate. And then instead of taking the first branch, you're going to take the ith branch. So okay, so my theorem is here the Hubbard, so if you take the ith branch and you play the same game along that vein, then the components of period km plus I, the components of the period I mod n, are all going to be spiral graphs. And moreover, the way that you're going to merge the N-Sharkovsky ordering along that vein is going to be coordinated by the ith branch. And the way that you can prove this is by using the fact that the internal address on these components are exactly going to be the only difference between this and the principal components of period km plus 1. The only difference between those internal addresses is going to be the very last term. And so if you follow the algorithm to construct the Hubbard tree, you get exactly a spiral graph. And if you get the spiral graph, then you know the set of periods that contains are exactly all the things that are less than or equal to whatever that period km plus I is. So this is the statement for these non-principal secondary veins. So the ordering of the components along that vein, of the I mod n vein, exactly corresponds to merging the N-Sharkovsky ordering so that it's coordinated by the I mod n branch. And then finally, you can explicitly determine the ordering along some of these veins. So I told you how you can get them via this way of coordinating by merging along the ith branch of the N-Sharkovsky ordering. And in some situations, you can determine the ordering explicitly. For instance, if n is going to be 2 times I or 3 times I, or you have the 2i mod 3i branch. And this just comes from the fact that if you do that, because there are I mod n branches on top, and by definition of the N-Sharkovsky ordering, you can only get to the other ones that have a common factor with, or rather how do I describe it? Where the GCD is going to be the same GCD as this I with respect to your n. So because of that, in these particular situations, you can determine the ordering explicitly. And I think I will stop here. Okay, thank you.
Any questions or comments? I have a question. I don't know if that makes sense because I'm not a specialist, but given a certain sequence, is there a criterion to determine whether there exists a certain determined vein that corresponds to that?
What do you mean? Oh, so given a sequence of
integers or
is there a certain vein that
yeah, if you have an ordering, a certain ordering, is there a criterion?
I'm not sure. I think there are ways that you can so for instance, you can probably say something about, there not being such a vein via if you can reconstruct the vein, then you can say something about the internal address of the components that are along it. And I think if you should be able to rule out certain situations, and you
maybe you can say that it is not.
Yeah.
Okay.
Yeah, I haven't thought about that.
Okay. Are there any other questions or comments? Yes.
You said that the Hubbard tree contains all the interesting dynamics. Could you expand on that?
In the sense that, so the Julia set contains all the interesting dynamics, right? And essentially, for quadratic maps, the rest of the Julia set, the rest of the components that are not sort of touched on by the vertices in the Hubbard tree, they would eventually like fold on to the components in the Hubbard tree.
Okay.
So you don't really get any sort of like interesting dynamics outside of that.
Okay, so once you know the dynamics on the tree, you kind of know everything else.
You kind of know a lot of the interesting things. I mean, like the rest of it, what is it going to be? You just have like, you know, they will eventually map onto the tree, right? So, and then, you know, on the interior of it, it just contracts.
Thanks.
Any other questions or comments? No? So let's thank the speaker again. So next speaker is Divya Khurana. She will speak about analytic zero-entropy diffeomorphisms with weakly mixing derivative extension.
Hi. First of all, I would like to thank the organizers for giving us the opportunity to talk here. And unfortunately, I missed the chance to be around there. Anyway, hopefully next year I will join you all. Sure. So, okay, in this talk, today I will talk about ergodic. We will explore the ergodic properties of the map along with its derivative map. We will construct an examples of a smooth dynamical system, which is a weakly mixing and having extra complex dynamical behavior along with it, and also find the analytic counterpart of such transformations. So this work is based with Shilpak Banerjee and Philip Kunde. So before that, I will talk about little about the smooth ergodic theory. So this subject study about the ergodic properties of the smooth dynamical systems on the Riemannian manifolds with respect to the natural invariant measure. So here we mean by natural is like the most physical measure, Riemannian volume measure, or the Borel measure, or which defines the volume of the measures. And the history of this subject, the smooth ergodic theory, is as old as the abstract ergodic theory. It begins with the Boltzmann hypothesis, ergodic hypothesis, which was firstly formulated in 90s in the Hamiltonian mechanics. In 19th century, then the work of Birkhoff and von Neumann comes on for the ergodic theory, ergodicity and fundamental ergodic theorems was defined. In the beginning of 1930, the study of smooth dynamical systems are being studied for the geodesic flows for the negatively curved surfaces. Then in the beginning of 1950, Kolmogorov and Arnold and Mazur developed a new perturbative theory where they have found an obstruction to the ergodicity in the Hamiltonian systems. And then in 1960, Anosov and Sanai's work on the hyperbolic system gains an intense activity in this subject, and the study expanded in various other subjects. Even the weaker notion of hyperbolicity has well understood, and KAM theory got used in the broader context, and the study expand, and the subject expand in the various other direction and intensively active. So one of the major problem, one of the famous problem of the smooth ergodic theory is asked by the von Neumann in his foundational paper in 1932, is the smooth realization problem. So the problem was seeking like, are there exist smooth counterpart of the objects or the concepts of the abstract theory? So if there are some concepts or some maps that exist for the abstract ergodic theory, can we have a smooth counterpart on this for the similar? Or maybe if you have a smooth measure preserving system, can we have a smooth, if you have a normal given measure preserving system, can we have a smooth measure preserving system along such that these two systems are conjugate? So the problem was looking around, like, does there exist a smooth diffeomorphism on the smooth compact manifold, such that, which is a measure preserving with respect to the smooth measure? That is like the smooth measure would be equivalent to the volume measure, and such that the abstract system are to measure theoretically isomorphic. And the another sub-problem of this smooth realization problem is asking for existence of measure preserving diffeomorphism with specific ergodic properties. In other words, one can ask, does the ergodic property can be also realized on the smooth manifolds or not? Or every smooth manifold can have all the ergodic properties can be realized. So there are some examples of realizing such ergodic properties on different manifolds. For example, the first example was constructed by Bainasov and Katok in 1970, where he constructed the area preserving ergodic smooth diffeomorphism on the disk. So he realized the ergodicity and the smooth diffeomorphism on the disk, which is measure preserving as a area preserving. And further, Windsor in 2001 realized the minimality but not uniquely ergodic. He constructed more than one number of ergodic invariant measure in his construction on the torus. And subsequently, Fayad-Sapkina and Windsor in 2007 constructed a uniquely ergodic, realized the unique ergodicity on the torus. And many other ergodic property then further get realized on different smooth manifolds. So after realizing the smooth maps, can we extend this class of maps for the derivative extension as well? So if we have can we realize the ergodic behavior for the map along with its differential map as well? Can we have ergodic behavior for the base point and as well as its tangent vectors along? So the class is called the derivative extensions. So maybe first I will introduce what we want as a projectivized derivative extension, what we mean by. So for a smooth map, if we take its differential map along with the map from the tangent bundle to tangent bundle, we call that map as a derivative extension. And corresponding to a point on the base, on the manifold, if we identify that tangent space with the Euclidean space and consider its projective space. So for example, then we call that space to be a projective tangent bundle. And the map would be called F, df to be a projective tangent bundle to the projective tangent bundle. For example, I have drawn a picture behind me. If you can see, there is a manifold corresponding to every point. There is a tangent space and we have projected it and consider its projective space. That would be a T1. So it will be a circle corresponding to every point. You can define its fiber. So similarly, for every point, and if you take a map, the point will be moved to another point, and as the fiber points will also be moved to, will also be made. So as we have defined this projective derivative extension, now one wants its invariant measure or the what structure we want to next put on this space, nice space. So in Gunesh and Katok in 2000 showed that if the map is a measurable Riemannian metric, if it preserves the measurable Riemannian metric, then this projective map admits an invariant measure on the projective derivative extension. So in a way, if the map, it was saying to that existence of measurably Riemannian metric would be equivalent to existence of the invariant measure on the projective derivative extension. So he showed in his work, and then Gunesh and Kunde constructed in 2014, constructed realizes the weak mixing map such that it preserves the smooth measure and as well as preserve the measurable Riemannian metric. But the invariant measure that is defined on the projective map was not ergodic. Only on the base map was the weak mixing. The ergodicity was only achieved for that. Weak mixing and the ergodicity was only achieved for the base map, not for the whole. So it was natural to further explore the ergodic properties of this measure as well. So in 2020, Kunde realized the ergodicity for the differential map, where he constructed the ergodic and the weak mixing whose differential is also ergodic. And these were the only known example where the ergodicity was realized for the derivative extension. Now the question was to, can we realize other ergodic properties for such diffeomorphisms and derivative extensions? Can we, there could be many possibility like unique ergodicity, weak mixing, strong mixing, or maybe number of invariant measure one can study on such spaces. Even in Kunde's paper, he also asked, if we have a differential derivative is ergodic, can we also find the real analytic counterpart of such map? That is, like, if there exists, does there exist a real analytic diffeomorphism whose differential is ergodic? So here we have realized the weak mixing property of such a measure. So we construct a weak mixing diffeomorphism whose derivative is also a weak mixing. With using analytic approximations and technique, we are able to upgrade the similar result for the analytic setup. And we achieved it, real analytic diffeomorphism whose projective derivative extension is a weak mixing. And all the construction, all the examples that we have discussed where the ergodic property is realized on the smooth manifold in this slides is achieved using this Anosov-Katok method. So this method is very versatile. So this method is basically allow us to construct the examples of dynamical systems, topological and measure theoretic system which satisfy interesting properties, means measure theoretic and ergodic properties. With the pre-described ergodic properties, we can also achieve with this method. And it was invented by Anosov and Katok in 1970. And this method is also known as approximation by conjugation. You will also see why the name is given to this method. And there are many examples that has been constructed in the smooth dynamics, especially for the smooth dynamical system using this method. Even the first example was the construction of area preserving smooth diffeomorphism on the disk was constructed using this method. Even that thing was even 90s, 70s was, before that was not achieved. So this method, so here is the overview of this method. The only need that you want in this method is like the smooth manifold that we are constructing has to have a non-trivial circle action on. There are many other methods available for the measure preserving systems, like interval exchange methods, but it is one of the rare methods that is available to construct the smooth examples in the smooth dynamics. So here, so the overview is like, we consider, let ST be a circle action, which is defined as a translation in the first coordinate by the parameter t on the torus. This method I'm just only discussing for the torus, and the same got extended to the another manifolds as well. So this method involves, you define a sequence of diffeomorphism and you converge it, and the limit that you get would be your required smooth map, or the whatever be the target map that you are looking for. So this method involves construction of the required diffeomorphism as a limit of the periodic diffeomorphism, where the limit of the sequence would be taken in the appropriate topology. If you are looking for the map T to be a smooth, so you will look in the smooth topology. If you want in the measure theoretic, so you apply only that topology. And if you want your to real analytic, you see the convergence in the real analytic topology. So the Tn has a special form. It is defined as iteratively as a conjugation by the circle action, where circle action has a alpha n, where alpha n would be the rational numbers, and the conjugation maps capital Hns would be written as the composition of Hns, which have a specific property. They have to be satisfied. They have to satisfy. They have to commute with the previous circle action. That is the technicality that we needed to work this scheme. So at the nth level, you already have alpha n's, Hns, and the Tn's. And at the nth plus 1 level, you will construct the conjugation map and the rational maps. So first you construct the conjugation map such that it commutes with the previous circle action. And you choose your next rationals alpha n plus 1, so that if you look at the Tn and the Tn plus 1, so here we are just using the property of Hn plus 1 commuting with this previous circle action, and if you commute it back, you realize the Tn and the Tn plus 1 only differ by the circle action, which is the alpha n and alpha n plus 1. So in our case, it's a translation defined by the translation. So if you want Tn and Tn plus 1 to be very close, we want alpha n to be very close enough such that these two maps get very close, such that we get the convergence in the required topology. So the alpha n would be chosen such that we get the scheme to be convergent. So the key idea of this whole method is the choice of the rationals and the conjugation maps. So the choice of the rational will depend upon the convergence of the Tn's. The alpha n's will be chosen such that we get the convergence, and the conjugation map would be chosen such that the required dynamical property got transferred to the final map. So what actually is happening is, at each stage, the conjugation map is applied to the circle orbit, and each step the circle orbit get perturbative, and such that it will perturb the circle orbit and distribute the orbit in the whole space in the required sense, so that our dynamical property would be satisfied on a finite level by the Tn's. And then under the final asymptotic version of that property got transferred to the final map. So here is a one interest. This method is very surprising. Like Tn's, you are starting with the periodic transformation or the periodic orbits, and then you are converging to, you can have a flexibility to converge to a aperiodic behavior. So okay, here I would like to give a little sketch of the proof that we have, the result that we have proved. So we construct a smooth diffeomorphism, which is the measure preserving, and whose derivative extension is a weak mixing. So the idea is very simple. So we take the torus and partition it into the small squares and the rectangles of distinct size with distinct aims. And we define the conjugation map over such on the torus. And we define it as a composition of two maps, phi n's and the gns. So these two maps are defined with a distinct aim so that they achieve a different kind of distribution. So phi n will rearrange the squares and the rectangles to meet the weak mixing criteria, will define a particular kind of distribution of the elements, and gn will do the different distribution. It is defined as a shear function on the theta direction. So once the phi n will be acting, it distribute the squares or the elements of the torus in such a way we meet some certain criteria of distribution, and then further gn will be applied so that it further distribute in the required sense, so that the hn satisfies certain combinatorics such that fn comma dfn will satisfy the finite version of weak mixing criteria. And then we will show this sequence is converging and converging in the required topology, and the limit f comma df is a weak mixing. So here is the key idea, or like a example of a distribution of an example distribution of the elements can look like. So here we define our conjugation map as a composition of, again, two different distinct functions, so that two different aims can be achieved. So one is our base and one is the tangent vector, the fibers along that. So phi n tilde we define such that it moves the squares and the rectangles over the torus, such that we get the weak mixing or distribution behavior on the base manifold. And then we have a ion map, which basically does is rotate those squares and the rectangles in a particular direction with a particular angle, so that their tangent vector get rotated. Once they are rotated, and we have specifically defined different regions and where the ion will act different angle here and different angle there, so that you get the distribution along the tangent direction as well. So maybe you can look at the figure as well. If you look at the top of the left, you see the example of the ion. You can see on the torus, there is a two small squares C and D. They are two different base squares on the base manifold, and there is a attached circle to that. That is a projective tangent space, and there are tangent elements that we had defined. And under the ion transformation, they are being rotated with different angles. For example, the T that you look here will go two times down, whereas I goes 5 and 6 times, couple of times goes down. So the different angles are being, different rotations are being applied to different regions to get the distribution in the tangent direction. And overall, the ion is acting as you can see in the down picture. So you see the first row of the leftmost, the figure A got transferred with the small squares, got transferred to the first column of the right, and with zero rotation of the squares. Whereas the second row got transferred to the second vertical row of with the slightly rotation of the squares. Whereas the third row of the left got transferred to the third vertical row with more rotations. In this way, we achieve the distribution on the base as well as on the tangent vector. And there are many other technical things and needs to be satisfied, but this is the core of the idea, that the distribution idea has to be taken to picture. So yes, and here are some useful references that I have used, and this work is just around the winding up. It will be archived by, I think, within 10 days. So I will share the link sooner. For now, I don't have the link for that, but I will share the slides if you want. Okay. Thank you for your attention. I hope I have not
Are there
exceeded
any
my-
questions or comments? Yes.
For the system that you just explained, the construction, do you know the weak mixing speed?
Weak mixing?
The speed of.
No, we are not capturing. We are not capturing the weak mixing speed.
Another question. So in GN, the almost last slide. So you said that there is a sharing by theta. Is it the same theta each time?
No,
or
no,
is
no.
It, okay. So
No, it's a direction, like theta and r to be directions. So the shear function is basically defined as a translation map in the theta direction, in the first coordinate.
okay, thank you.
Maybe this notation is more confusing, I think so.
Thank you, very nice talk. And what about flows? Does it make sense? The question for flows?
Yes. Why not? Yes.
I have yet another question. Are there any known obstructions to the, given that the base is weakly mixing, for the extension, derivative extension to be weakly mixing? I mean, does the fact of the extension be weakly mixing imply anything about F?
Can you recall?
Yes.
Repeat
Are
your-
there any known obstructions, given that F is already weakly mixing, for the derivative extension to be weakly mixing? I mean, does the fact that the derivative extension is weakly mixing imply anything about F?
Yes. Then the base will automatically be weakly mixing.
Yes. But besides that, because there are examples where you have weakly mixing and the extension is not.
Yes, because we are not able to distribute the elements in the tangent directions.
Yes, but my question is, do you know any specific obstructions besides being weakly mixing, being the base weakly mixing?
No, so the point is to get the distribution in the tangent direction only.
Okay.
So your system is weakly mixing but not mixing, right?
Yes, no, not strong mixing. Even the Anosov-Ketov method, from that you cannot achieve the strong mixing, because if you see the TNs are periodic behavior. After every Qn times it will repeat its behavior. So it's impossible to achieve the strong mixing for any case from this method.
Okay.
And I don't know other methods to achieve such a construction.
Okay, are there any other questions or comments? Okay, so let's thank the speaker again.